studying atomic energy, we could begin with a bomb. But since we must learn about atoms themselves, we can begin with a bubble. For bubbles, like all matter everywhere, are made of atoms. If we could cut a bubble in half, and if we could enlarge the thin shell millions of times, we would see countless small particles called molecules. Within these molecules, we would find atoms. The hydrogen atom, for example, the simplest atom in nature. It consists of two parts. One is a light particle with a negative electrical charge called an electron. The other is a nucleus consisting of a heavy particle with a positive electrical charge called a proton. Almost all the weight of the atom is in the proton, which weighs almost 2,000 times as much as the electron. Slightly more complex is the helium atom. This atom has two electrons and a nucleus containing two protons and two particles called neutrons. A neutron weighs about the same as a proton, but has no electrical charge. It can be thought of as an electron and a proton combined. Again, the helium atom has a nucleus of two protons and two neutrons, and there are two electrons in outer orbits. Now let's look at one helium atom together with four hydrogen atoms. Notice that the four hydrogen atoms contain all the parts needed for one helium atom: an electron and a proton, an electron and a proton and electron combination to form one neutron, and another such combination to form a second neutron. By a complex process under special conditions, this net change can take place. When it does, there is always a loss of weight. Four hydrogen atoms weigh this much in mass units. The helium atom weighs this much. This weight is lost in the process of combination. What happens to it? Suppose we have on a scale an iron ball at a temperature just below the melting point. As the ball cools, it loses a slight amount of weight. In cooling to room temperature, a 5-foot ball will lose 5 milligrams of weight. The weight is given off as radiant energy. Similarly, the weight lost when helium is formed from hydrogen is given off as radiant energy. Notice that this process involves nuclear changes. Starting with 4 hydrogen nuclei of 1 proton each, we end with 1 helium nucleus of 2 protons and 2 neutrons. This process is called nuclear synthesis. It is one way of releasing atomic energy. It is this process, occurring with billions upon billions of atoms, that produces the energy of the sun. Every second, the sun loses over 5 million tons of mass in the form of radiant energy produced by atoms of hydrogen combining to form helium. This atomic energy of the sun is the source of virtually all the energy used on Earth. The sun's energy reaching the Earth has several effects, but perhaps the most important is its action on growing plants. Plants convert solar energy into chemical energy by a process called photosynthesis. How does this chemical energy differ from what we call atomic energy? If we could look inside this tremendously enlarged leaf, we would find molecules which, in turn, are composed of atoms. But whether the atoms be of hydrogen or some other element, chemical changes never affect their nuclei. Only the electron orbits are changed. In photosynthesis, the actual changes are extremely complex, but the general principle can be seen in a simple example. Let's consider this a hydrogen atom at room temperature. Now, if it is subjected to enough radiant energy, a point is reached at which the electron jumps to a larger orbit. The atom now has more energy than when the orbit was here. If the electron jumps back, it gives up the energy it acquired. Somewhat similarly, in photosynthesis, solar radiation raises electrons in the green coloring matter of plants to higher energy levels. And it is this energy that is liberated in combustion. But here too, as with all chemical energy, only electron orbits are affected. For many years, however, we have known of another form of energy on Earth. Radium, for example, gives off energy spontaneously. Let's look at the radium atom. And let's consider the nucleus only. Notice that it consists of a great many protons and neutrons. Now this nucleus is unstable, and over a long period of time undergoes various changes that liberate energy. Notice that the changes here are in the nucleus. This is natural radioactivity, another way of releasing atomic energy. As it occurs in atom after atom, the radium gradually becomes lead. The entire process takes years, and the energy released at any given moment is relatively small, though not insignificant. This is the most complex atom found in nature, the uranium atom. And this is the uranium nucleus. If it is bombarded with a neutron, say, it splits apart. This process, called nuclear fission, liberates a relatively large amount of energy, mainly as the energy of motion of the fission particles. These particles, after fission, weigh 2/10 mass units less than the same particles before fission. The mass lost is given off as energy. Notice that a free neutron can start the process, and that other neutrons are freed by the process. These neutrons can go on to split other nuclei. One fission can produce two. Two can produce four. Each of these can continue the process. This is called a chain reaction. Under the proper conditions, which in practice are very difficult to achieve, it continues until the uranium fuel is largely burned out. For clarity, energy waves are not shown here, but remember that each fission also releases some radiant energy. Even where billions of uranium atoms are involved, the entire reaction takes less than a millionth of a second. This is what happens in the atomic bomb. This is the larger process. The bomb creates extreme heat. This heat causes the surrounding air to expand with tremendous velocity, producing a violent explosion. The release of atomic energy in this form is new, but for billions of years, the sun has released atomic energy through nuclear synthesis. The sun's atomic energy has been stored on Earth as chemical energy, which we can liberate through combustion. For years, we have known of the release of atomic energy in the form of natural radioactivity. But now we have learned to release atomic energy through nuclear fission. From this has come the atomic bomb. What is yet to come, no man knows.